Okay, today, oops, where did I put my notes? Today, you guys, we're going to learn about center of mass. We're going to define what the center of mass is. We're going to learn about 3 ways that you can physically find the center of mass of something. Then we're going to learn a mathematical way to find the center of mass of things, and we'll do that. And then we're going to talk about the velocity of the center of mass. That is the motion of the center of mass of the system. You'll learn a mathematical way to find the velocity of the center of mass. And then finally, you'll learn that the velocity of the center of mass of an isolated system does not change. It just maintains whatever velocity it had. But first, let's define what center of mass is. Center of mass is the average location for the total mass of a system Now, if you're a normal person, this shouldn't really make a lot of sense to you. But as we talk about the 3 ways to physically find center of mass, then you'll start seeing more and more what this means. So let's go ahead and do the 3 ways to find center of mass. And do you mind if I call center of mass just CM? Center of mass, CM. 3 ways to find CM physically. First, center of mass is always above the support point. Sorry. So, look at this meter stick, okay? 100-centimeter meter stick. It looks uniform. So tell me, where do you suppose the center of mass of this 100-centimeter meter stick is going to be at?
50 centimeters.
How many people thinking at the 50? Sure, and we can tell that's true because I can balance this meter stick at the 50-centimeter point, right? It balances at this 50-centimeter point because the center of mass is always directly above the support point. I'm supporting this system at the 50-centimeter, which means the center of mass is directly above it, just as you'd expect. But how about for this hammer? Where do you suppose the center of mass of the hammer? Is it going to be right at the middle like it was for the meter stick? No way. If I put my hand there to support it, what's it going to do?
Fall.
It's going to fall, right? Because where's the center of mass going to be? Yeah, how many people thinking closer to the head? Because that's where all the mass is, right? The center of mass is the average location for the total mass of the system. Well, since most of my mass is concentrated here, I would expect the center of mass to be close to there. And in fact, it is. I can balance this hammer. I find it very hard to balance this hammer. But you see where my support, there it is. Oh, wait. Stupid thing. Oh, whatever. God, why is it so? But hey, you get it, right? The center of mass is pretty darn close to the head, okay? Directly above the support point. There's another way to find the center of mass of a system. The center of mass is directly below the point of suspension. Now, I'm not going to support this meter stick by putting my hand below it, okay? I'm going to support the meter stick by hanging it from a rope or a string. You see that? I'm now suspending it, but still my suspension has to be at the 50-centimeter point, right? At the middle of it. And then it'll be suspended. And the same sort of thing with my hammer, correct? If I decide to suspend the hammer from my finger like this, do you see how it's now suspended? Then the center of mass will be directly below the point of suspension. You guys okay with that? So, for example, when someone draws a person climbing a rope, here's the rope, and here's the person climbing the rope, okay? This is not an accurate drawing because this person is essentially suspended from this point, and his center of mass has to be directly below that point of suspension. When a person is climbing a rope, what they actually look like is something like this. If they're climbing it with just their hands, okay, and then here's the rope. You see what I mean? Where their body is actually bent in such a way that the center of mass of this person has to remain directly below the point of suspension. You can't climb a rope like that. You can climb a ladder like that, but not a rope. Alrighty. Hey, there's a third way to find the center of mass. The center of mass is point about which this system spins so for example, we've already established that the center of mass of this meter stick is at the 50, correct? So if I were to spin this meter stick in the air, what point would I expect this meter stick to spin about? If you're thinking the 50, you're correct. Oops. But you guys see that this is spinning about the 50. You know, it's spinning and it's looking symmetrical as it spins. Why am I such a spaz? Oh, here we go, I'm catching it now. Okay, you guys okay with that? It's spinning about the 50. If I go really fast, you can see it. It spins about the 50. Okay. But what about the hammer?
No.
What point is the hammer going to spin about?
About the head.
Yeah, about the head, about the center of mass. Do you see that? It kind of looks like wobbly. It's not spinning symmetrically like the meter stick does. It's spinning about the center of mass.
Much better with a hammer.
Yeah, I'm better with a hammer than I am with a stupid meter stick. So you guys seeing that okay? That wobbliness. Okay, they're spinning this meter, all of the points, all of the mass of the system is spinning about the center of mass of the system. One situation that you're familiar with, which is really important, is the Earth and the Moon, right? The Earth the Moon does not just orbit the Earth. Actually, the Earth and Moon are a two-mass system. Imagine that they're connected by this massless but infinitely strong, infinitely rigid bar, but a massless bar. The Earth and the Moon are just spinning through space in the same way that hammer spun through the air, right? So if you could find the center of mass between the Earth and the Moon, which you're actually going to do on one of tonight's problems, you'll find the center of mass between the Earth and the Moon. That center of mass ends up being within the Earth, but it's still there. The center of mass of the system isn't the center of the Earth. So tell me, what's the Earth and Moon going to look like as they orbit each other? Anyone thinking they're going to look like the hammer?
Yeah.
Yeah, so the Earth is wobbling. So really, there's three types of motion the Earth has. The Earth is spinning about its axis. The Earth is revolving around the sun. But also the Earth is revolving around this point, the center of mass between the Moon and itself. You know? In fact, let me give you another question. Suppose we're looking at a star that's really, really far away. So all you see is this little point of light, that star. How is it the scientists are able to tell that star has planets orbiting it? I mean, planets aren't luminescent. You can't see a planet from far away. You can barely see the star. How do we know that star has planets orbiting it?
Base times movement.
What's that?
Base times movement.
Tell me more. What's the star doing? Yeah, it's wobbling, right? You're looking at the star. If the star has no planets orbiting it, that star is just going to stay there. But if that star's got planets orbiting it, then that star is going to wobble as the planet orbits it. Because really, when a planet orbits a star, the planet and the planet and the star are actually orbiting the center of mass between them. So that star is orbiting the center of mass. Now, of course, if the center of mass is within the surface of the star, then it essentially just looks like the star is wobbling, just like our Earth is wobbling back and forth. Is it, when the moon is there, the Earth is here. When the moon is way over here, now the Earth is over here. And so it looks like the Earth is just wobbling, But it's still orbiting the center of mass, the mutual center of mass between moon and Earth. So is that okay with the 3 ways of finding center of mass? And I'm hoping that this is giving you more insight into what center of mass is. Because now we're going to do math. We're going to do not center of mass, we're going to do center of math. Because there's math, baby. Here we go. Okay. Let all distances x be measured from any arbitrary 0 point. We get this, the location of the center of mass, which I'm going to call x sub cm, x meaning like the location, like, the meters or whatever, cm meaning center of mass, ends up equaling the sum as I goes from 1 to n of m sub I x sub I over the sum as I goes from 1 to n of m sub I. Now, most of you probably are not comfortable with sigma notation, so I'm just going to write it out. This is going to be m1 x1 plus m2 x2 plus ... As many objects as you have in your system, that's how many m1 x1s and m2 x2 and m3 x3. And this is going to be over just the sum of the masses. I'm going to do an example of this, and then I'll have you guys do an example. Suppose I've got a meter stick, and at the 10 centimeter point, I balance 200 grams. I put 200 grams at the 10 centimeter point, and I put 500 grams at the 90 centimeter point. Here's 50 centimeters. Here's 0. I want to find the center of mass of this system, the center of mass of the 200, 500 gram system. Well, you tell me, halfway in between them is 50. But this is 500 grams and that's only 200 grams. So where would you expect the center of mass to be? On this side of the 50 or that side of the 50? How many people say that side of the 50? Okay, yeah, good for you guys. Because there's more mass there. So the center of mass, would be driven to the right by the fact that there's more mass there. Well, let's go ahead and get the position of the center of mass. And if the position is going to be relative to any arbitrary 0 point, what point would you like to choose as your arbitrary 0 point? Okay, I heard some person say 10. Is anyone thinking choose 0 as your arbitrary 0 point? Okay, that's what I'm going to do, even though it doesn't matter. I'm going to choose 0 as my arbitrary 0 point, so that the first mass, 200 grams, is 10 centimeters away from my arbitrary 0 point. And the second mass, the 500 gram mass, is 90 centimeters away from the arbitrary 0 point. And then I've got 200 grams plus 500 grams in the denominator. Do you see that the numerator is in the units of grams centimeters and the denominator is in the units of grams? So the grams cancel, leaving you with just centimeters. And if you do the punchy, you end up with 67.1 centimeters. That is, I should be able to stick my finger right there at 67.1 centimeters and balance those two masses, because that's where the center of mass is, 67.1 centimeters. Any question or issue on this? By the way, would I have gotten a different answer if I chose 10 to be my arbitrary 0 level? Yeah, no way, because now this becomes a 0. If 10 is my arbitrary 0 level, that's a 0 and that's an 80, and I end up with 500 times 80, which is 40,000 divided by 700, and I get 67.1. So I want you to see I could choose any point as my arbitrary 0 level and get the same answer. I am now going to demonstrate this. And boy, will you be impressed when it works out perfect and I'm able to balance this at the 67 thingy. Yeah, I need to have it looking like that. Here we go. I'm going to hang my two masses by string. Okay, here's the 500 gram mass, and I'm hanging it right on the 90. I don't know if you can see that from where you are, but I'm hanging the 500 gram mass right on 90. Okay, and then I'm going to hang the 200 gram mass right at 10. So it's right at 10. There it is. So as you see, it's hanging at 90 and 10. Okay, and then I'm going to put my finger right at 67.1, and boy, will you be amazed when it balances. 67.1. Wait. Shoot. Just a second, that's right at 90. That's right at 10. But it balances at 65. So does that mean science is a lie?
Yes.
Because it should be 67.1, but I'll tell you, I'm looking at it right now, it's 65. Or is there something I'm forgetting here? What? Who said that? Cheyenne, say that again.
The mass of the ruler.
Yeah, the mass of the meter stick. This is not a 2-mass system, this is a 3-mass system. I've got a meter stick involved here as well. And I'll tell you right now, I've measured it before the class, this is a 100 gram meter stick. Okay, it's 100 grams. So really, this isn't a two mass system. This is a 3-mass system. And you tell me, where do you suppose that 100 grams for finding center of mass, because this is an evenly distributed 100 grams, where should I say the 100 grams is concentrated at?
50.
Yeah, 50, right? So it's your guys' turn. This isn't a 2-mass system, no siree. It's a 3-mass system, where you've got 100 grams right at 50. So please now, in the same way that we did that one, go ahead and find me the center of mass. 3 masses, 200 grams due to the mass, 500 grams due to the mass, and then 100 grams at 50 centimeters because of the meter stick itself. Good luck. I'm going to use, myself, I'm going to use 0 as my arbitrary 0 again. What'd you guys get? You should be getting precisely 65, which is what happened when I balanced it on my finger. It was exactly 65. Yes.
So if you were to change your arbitrary 0 point, that would also change your answer in a way, but then you have to account for where you put your arbitrary 0 at?
Absolutely.
Okay.
Yeah, so if your arbitrary 0 point was at the 10, then this guy ends up being 55. Oh, I guess I didn't make that clear. My bad. Yeah. If you change your arbitrary 0 point to 10, that'd be 55. So, I'm so bad. Mr. Shana lies again. But this, if you changed it to 0, so that's just 800 over 700, 80,000 over 700, then this becomes 57.1 instead of 67.1 because you change your arbitrary 0 point to 10 instead of 0. My bad. Oh my God, I'm such a liar. Well, the whole world sees it now. But it doesn't matter. People lie all the time. All right. Hey, any questions? Anyone not getting 65, or if you chose 10 as your arbitrary 0, 55. Anyone not getting those? Anyone need to talk about this? Yes?
I have a question. So if your arbitrary 0 point is 10, are you basically saying like the meter stick is like a smaller distance?
No, you're just saying that all of these guys are measured relative to your arbitrary 0 point. But that's not saying anything about the length of the meter stick. Yes?
If you wanted to make your arbitrary 0 50 centimeters, would you have a negative for where the 10 is, or would it just be
Yes.
a positive because it's a distance?
No, it'd be negative. It'd be a negative. Yeah. Good for you. Yes?
So could I always just pick 0?
Yeah, sure. You can do whatever you want. Yes?
So you can balance it at 55 as well, and you can put the arbitrary 0 at 10.
Yeah, isn't that weird? Yeah, yes. If I put my arbitrary 0 at 10, then on the meter stick I'd be at 65, but that'd be 55 to the right of the 10.
Oh, so it's still the same.
Yeah, it'd still be in the same place.
okay.
It's just 55 centimeters to the right of the 10. Yeah, my bad. So glad thank you, Noel, you saved me.
Well, I
Now at
wanted to
least,
try it, and then I got a different answer, but then I noticed it was off by the amount that the arbitrary 0 was off of 0. And I had to
yeah.
ask.
Yeah, I wasn't thinking. I don't remember why I just said no. I knew that. I mean, I have it in my notes. Whatever. Okay, hey, it's time to talk about the velocity of the center of mass now. So here we go. The velocity of the center of mass, which I'm going to call V sub cm, we essentially do some mathematical trickery where we get the delta x and turn all these guys into delta x's, then we divide by t, but don't worry about it, I'm just going to tell you what it is. It ends up being m1 v1 plus m2 v2 plus dot 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 over m1 plus m2 plus dot dot dot. Okay, where you'll notice the numerator now is not m times the distance from an arbitrary 0 point. The numerator is now m times velocity. It's the mv of each of the points in your system, which the numerator ends up being the total momentum of the system. That's the numerator, and the denominator is the total mass of the system. And when you do the total momentum of the system divided by the total mass of the system, you get the velocity of the center of mass of the system. And one more thing I want to remind you, momentum is a vector. So you can have positive and negative momentums. You can have a situation where the total momentum of the system is 0, in which point the center of mass of the system isn't moving. Okay, let's do a problem using this formula. Suppose I've got here, whoops. I got an ice skater. He's a 100 kilogram ice skater. He's going in this direction at 3 meters per second. I've got an ice skater over here. Just a second. Why am I having trouble drawing this female ice skater? Okay. This female ice skater is going 2 meters per second, and she is a 50 kilogram ice skater. Well, it turns out, looking at just center of mass, right now the center of mass, because he has twice the mass of the girl, the center of mass is going to be 1/3 of the way between him and the girl. The center of mass is going to end up being right there. But I want you to see that that center of mass is going to be moving to the right, because he's going so fast and she's going so slow. Another way to think of it is the net momentum of the system is moving to the right. You know, he's got 300 kilogram meters per second of momentum. She's got negative 100. So the momentum of the system is positive 200 kilogram meters per second to the right. So since the momentum of the system is moving to the right, that must mean that the center of mass is moving to the right. So I'd like everyone right now to please use that formula. Get me what the velocity of the center of mass is. Good luck. Just total momentum divided by total mass. Remember, positive momentums add and negative momentums subtract.
Aw.
What you guys getting? You getting 4/3?
Yes.
Hopefully. 300 minus 100 is 200. 200 over 150 is 4/3. 4/3 meters per second. That's the speed at which the center of mass of the system is moving. So let's say this happens. Okay, before I go on, are you guys okay with that? Can I move on? Any question? Okay. Remember, the girl has a negative momentum. So it's not 400, it's 200. Okay, well, I'm going to say that these two hug. Okay, they slam into each other. They embrace in a warm, beautiful embrace. Okay, so here's the girl in his arms. And they go off at a certain speed, okay? And I can use conservation of momentum to find that speed. Initial momentum equals final momentum, right? The initial momentum, we already found that. That was 200 kilogram meters per second. The final momentum is going to be the two of them together moving off at some speed. Tell me, at what speed do the two of them move off together? Is everyone getting 4/3?
Yeah.
Why would that make sense? Why would it make sense that when the two of them slam into each other and embrace each other, they would be going off at the speed of 4/3 meters per second? Well, what was the speed of the center of mass before they slammed into each other? 4/3 meters per second. Where's the center of mass now? Well, right there, because they're embracing each other as close as two human beings can possibly embrace. Thank you, Noel. That's right. She had to change the video camera because we weren't looking at them. Oh my God. Oh, these interruptions are so egregious. Hello? Yes, I do. Why? Okay. Will she know who Megan is? Okay. Okay, thanks a lot. Bye-bye. Brianna, they said you must go to the guidance office and see Megan.
Bye, Brianna.
But I don't know. Do you know who Megan is? Do you know who this person Megan is?
You just walk in the
They're gonna
office
see
and
you.
be like, which one of them is Megan?
Which one of these?
So, so you guys okay with this idea? Okay, I just want to make sure you get this. That the last thing I need to tell you is something, conceptual, and that is when you have an isolated system, the velocity of the center of mass never changes. Okay, so please write that down. Velocity of the center of mass of an isolated, and when I say isolated, that means the external force, the sum of the external forces equals 0. Okay? The velocity of the center of mass of an isolated system never changes. So let me ask you this one last conceptual question, and then we'll be done. Okay, here's Earth, and here's an asteroid. And let's say the asteroid is going 5,000 meters per second, hurtling towards Earth. We realize that asteroid is there, so we put a nuclear bomb on the asteroid, alrighty? And we blow the asteroid up into a bunch of little asteroid beds, asteroid thingies. Tell me, for this system, considering the center of mass of this system, how fast is the center of mass of that system going? I want to remind you, this bomb, once it's embedded in the asteroid, the bomb is part of the system. So when the bomb explodes, those are all internal forces that the bomb is creating. So how fast is the center of mass of that system going? I mean, within 5,000 meters per second. Yeah. I mean, it's still going 5,000 meters per second. Which means if all of those pieces hit the Earth, it's still going to be really bad. So if you're going to use a nuclear bomb to blow up an asteroid, what do you want to have happen? What's that?
It separates like the masses so that it makes them much smaller.
Okay, it makes the masses way smaller, like pulverizes them. Because then what happens if these little masses hit the Earth's atmosphere?
They're like,
Hopefully they burn up, yeah. They've got enough surface area that they end up burning up instead of hitting the Earth's surface. Also, what would you like to have happen to these little asteroid pieces?
keep them and sell them.
Yeah. Is anyone thinking like, I'd like them to miss the Earth?
Oh, yeah.
Like, are you thinking maybe when you explode it, hopefully these little guys go off like that, so that a bunch of them miss the Earth, they spread out, and then the Earth only gets hit by a fraction of them? That would be good. But I think collecting them and selling them would definitely be the best outcome. Okay, bye-bye.